Again, in this video, I'm going to go over this homework problem from 4.9. And so in this problem, it says, given the following acceleration function of an object moving along a line, find the position function with the given initial velocity and position. And so the acceleration function is equal to negative 26, which is just a constant function. And then the velocity evaluated at time 0 is 18, and the position function evaluated at 0 is 0. Okay, and then from that information, we're supposed to find the position function s of t. Okay, so let me show you how we can find it. So first of all, the position function is the antiderivative of the velocity function with respect to time. And the velocity function is the antiderivative of the acceleration function with respect to time. Okay, so what we're going to do is we're going to find the velocity function first by finding the antiderivative of the acceleration function. And then once we have the velocity function, we'll find the position function by taking the antiderivative of the velocity function. Okay, so let's find this velocity function first. Okay, again, it's the antiderivative of the acceleration function with respect to time, and the acceleration function in this case is a constant. It's just a negative 26. Okay, and if you want to find this antiderivative, one way of doing this is you can think of this as being negative 26 times t to the 0 power. There's kind of an imaginary t being raised to the 0 power. T to the 0 power is just 1, and so this is still equal to negative 26. But if you write it this way, then you can use your power rule to find the antiderivative of this. Okay, and so you could just add 1 to this exponent, and of course you would get t to the first power, and then you would divide by that number, so divide by 1, and you can see you just get t to the first power over 1, which is just t. And then you would multiply that by this constant. Remember, constants can come outside the antiderivative operator. So you may want to do that first. And then you can apply the power rule to this. And you'll just get t to the first over 1. And then times the constant, negative 26. Now remember, this is an indefinite integral, and so when you have an indefinite integral, there's actually a whole family of antiderivatives. So don't forget, there can be any constant added to this, and it would still be an antiderivative of negative 26. So there's a whole family of antiderivatives for negative 26. Okay, so this is our velocity function. And then because we're told this initial condition, we're able to solve for c, for the constant. Okay, so we're told that v evaluated at 0 is 18. And so if you plug a 0 in for t on for the velocity function, then you can see that you just get c. So v evaluated at 0 is just c. And that means c has to equal 18. Okay, and so we know this velocity function is negative 26t plus 18. Okay, because c must be 18 in order to satisfy this initial condition. Okay, so this is our velocity function. Okay, and now that we have the velocity function, we can find the position function just by finding the antiderivative of the velocity function with respect to time. Okay, and so this is our velocity function. And again, if you want to rewrite this as 18 times t to the 0, that might be helpful. And that way you can use the power rule to find that antiderivative. Okay, and so let's just apply the power rule. Now the constants can come out in front of the antiderivative operator. Okay, and then you would apply the power rule to the t here and the t to the 0 there. So let's apply it here. So you would add 1 to this exponent, and you get t squared, and then you divide by 2. And then that gets multiplied by the constant. Okay, and then this one, of course, you get add 1 to the exponent, you get t to the first, and then you divide by 1, so you just get t times 18. Plus some constant, and I'm just going to call it k because it might be different than the c here. Okay, and then let's just simplify this first before we solve for k. This is negative 13t squared plus 18t plus some constant k, and that is our position function. Now we're told that when we evaluate the position function at t equals 0, we get 0 for the position, right? S is 0 in that case. And so let's plug 0 in for t here, and when you do that, you just get k. Okay, and we know S evaluated at 0 is 0 because we're told that, and so that must mean k is 0 itself. And so knowing that, we can substitute 0 in for this k here, and we have S of t. So it's negative 13t squared plus 18t plus 0, right, because k is 0. Okay, so that's our position function. Now, if you want to check this, there's an easy way to check this. We know that the velocity function is the derivative of the position function with respect to time. And so if you take the derivative of this, you'll get negative 26t plus 18, which is exactly the velocity function. And then if you take the derivative of the velocity function, you'll get the acceleration function. So if you take the derivative of this, you get negative 26, which is the initial acceleration function that we were given. So you could always go back and sort of check this by taking the derivative of the position function and making sure that it's the velocity function that you found here. And then you can take the derivative of that velocity function and make sure it's the acceleration function that they gave you initially. Okay, so I hope you found this video helpful. If you get a chance to look at some of the other homework problems I have on video from this chapter, that would be good. And thank you for watching, and I'll see you next time. Bye-bye.